Welcome to the deep dive. I'm really glad you could join us today. We're tackling something super important in this session. We're calling it Exposing the Truth in the Digital Evidence. Now, this deep dive is especially for you if you're a Dr. Sam Pack College of Business student, maybe in management information systems, information technology, or computer information systems. We're really focusing in on computer forensics today. But honestly, the stuff we're covering is fundamental for pretty much any college student or, frankly, any working professional who's interested in digital investigations. Okay, so our mission today is to unpack the key ideas from Chapter 5, Working with Windows and CLI Systems. It's from that great textbook by Nelson and Stewart. Think of this as maybe a shortcut, a way to really get a handle on the digital landscape, pick up some surprising facts, some practical insights you'll definitely need. And hey, before we really jump in, please do like, subscribe, follow us, maybe share this deep dive, and definitely comment. We love hearing your thoughts and questions on it.
Absolutely. And, this isn't just abstract theory we're talking about. Understanding how data gets stored, how it's managed on Microsoft systems, well, that's the absolute foundation for digging up the truth in any digital investigation. It's how you recover files someone thought were gone forever, or how you make sense of an encrypted drive. This is where the real detective work starts. It's a pretty powerful skill set.
That's a perfect place to kick off. So let's get right to the core of it then. Why is understanding file systems and operating systems, the legacy ones and the current ones, why is that so critical for data recovery and digital investigations? What are we fundamentally trying to do?
The number one goal, above everything else, is to avoid changing the evidence. Simple as that. Think about it like a physical crime scene. You wouldn't just barge in and start tidying up.
Right, it's of course.
Digital data is exactly the same. A file system is basically the OS's map to find data on a disk. The second you power up a target machine the wrong way, or even just access a file incorrectly, you risk changing timestamps, maybe overwriting something vital. Knowing that roadmap, that structure, helps you navigate without contaminating the very thing you're trying to find. It's rule number one in forensics: do no harm.
That crime scene analogy really clicks. Okay, so before we even get to that roadmap, the file system, we need to deal with the computer's startup, right? The boot sequence. You mentioned needing to maybe access or change settings like CMOS BIOS, EFI, UFFI. Why are those initial settings so crucial for an examiner?
Right. Well, the CMOS chip, for example, that's where the basic system configuration lives. Date, time, boot order. That stuff stays even when the power's off. Yeah. Then you have the the newer EFI, UEFI. That's the firmware, kind of the intermediary, managing how the hardware talks to itself at a really low level. Yeah. Now, here's the non-negotiable part for forensics. You have to boot the suspect computer using your own forensically sound media, like a special CD, DVD, or USB drive.
Why is that so absolute? Why not just boot from its own hard drive?
Because the moment you let the original hard drive boot, the operating system wakes up and starts doing things. It writes temp files, updates logs, changes access times. You'd basically be trampling all over your digital crime scene before you even started looking. Yeah. It's all about maintaining the integrity of that data from the very first second.
Controlling the environment.
That's right.
So once we have that control, then we can start looking at the physical disk itself, those spinning platters coated with magnetic material. What are the key physical parts we need to visualize?
Yeah, visualizing helps. Think about the drive's geometry. That's its physical structure. Platters, tracks, sectors. The head is the little arm that reads and writes. Tracks are the concentric circles, like lanes on a racetrack where the data sits. A cylinder is just a vertical stack of the same track across all the platters. And each track is sliced up into sectors, usually 512 bytes each. Knowing this physical layout, it's like having the blueprint. It helps understand why data might end up in weird places, or why recovery is sometimes tricky. And there are finer points too, like zone bit recording, ZBR, where outer tracks hold more data, or head and cylinder skew, which helps speed things up. These design choices affect where data lands physically.
Fascinating. So the physical design itself impacts what we might find. But that's traditional hard drives. Solid-state drives, SSDs, they're a whole different beast, aren't they? What makes them different for forensic investigators?
Oh, completely different. The big one for forensics is wear leveling. See, flash memory cells in an SSD can only be written to so many times before they wear out. So wear leveling is this internal process constantly shuffling data around, trying to spread the wear evenly across all the memory cells.
Okay, good for the drive's lifespan, but sounds tricky for finding specific data.
Exactly. It means data isn't static, it's moving. That's why getting a full forensic copy, an image of an SSD as soon as possible, is absolutely vital, especially if you hope to recover anything from unallocated space. Another key thing, SSDs often hold a bit of an internal charge for a short while after power down. This can keep data, even in unallocated space, alive a bit longer than on a spinning disk. That makes them really interesting for mobile forensics. You might recover deleted texts or messages that haven't been fully cleared yet. It's surprising what can stick around.
Wow, okay, that changes the game quite a bit. Let's shift from the physical hardware to the logical structure now. Microsoft File Systems. How does Windows organize data into these clusters you mentioned, and why do the size and numbering matter to us?
Right, so Windows takes those 512-byte sectors and groups them into clusters. That's the smallest chunk of space the OS will actually assign to a file. And the size of these clusters can vary a lot, from just 512 bytes, maybe up to 32,000 bytes or even more, depending on the drive size and format. For forensics, knowing they're numbered sequentially is key. NTFS usually starts at cluster 0, FAT starts at cluster 2. This helps map things out. It lets you distinguish between the logical addresses, the cluster numbers the OS uses, and the physical addresses, which are the actual sector numbers on the physical disk. Understanding that difference is critical when you're dealing with disk partitions. These are like logical subdivisions of the physical drive. Windows sets them up as primary or extended partitions, each with its own logical map.
Okay, so we have these logical drives, these partitions, but you hear about things like hidden partitions or voids and partition gaps. Are these real things investigators can find or use?
Oh, definitely real. Think of those voids or gaps as just unused space between the officially defined partitions. They're not allocated to any partition. It's totally possible for someone tech-savvy to use a disk editor, something low-level, to tweak the partition table and actually hide data in those gaps.
Yeah.
So from a forensic perspective, you absolutely cannot just trust what the operating system shows you. You've got to dig underneath.
And when you say dig underneath, where's the first place you look for that fundamental partition information?
The master boot record, the MBR.
Oh.
It lives right at the very beginning of the disk, physical sector 0. That MBR contains the partition table, which is essentially the master directory for all the partitions on that drive. It's ground zero for forensic analysis of the disk structure. Tools like WinHex, Hex Workshop, those become essential. They let you look directly at the physical sectors, ignore the OS interpretation, and see what's really there, maybe find hidden partitions or even file fragments.
That's powerful. Okay, let's get into the file systems themselves, starting with the original. FAT, the file allocation table. What was its main idea, and what clues does it offer investigators today?
FAT was Microsoft's first real file system structure. It's basically a database, usually stuck right at the beginning of the disk on the outermost track. It holds all the critical info about files, names, dates, times, where the file starts, the starting cluster, attributes, all that stuff. And it evolved. FA12, FA16, FAT32, then XFAT for bigger media, each version adapted. But the key forensic takeaway across all FA versions is how it handles clusters and leads to drive slack. See, Windows assigns space in whole clusters. If your file is, say, 1.2 clusters long, it gets assigned 2 full clusters. That leftover space in the second cluster, that's slack.
And that slack space isn't empty.
Not necessarily. You have RAM slack, which might contain leftover bits of data that were sitting in the computer's RAM when the file was saved. And then you have file slack, which is the rest of that unused sector space within the cluster. This slack space is an absolute goldmine, seriously. It can hold fragments of previously deleted files, bits of emails, passwords, anything that was recently in RAM or just got partially overwritten. It's like finding forgotten notes scribbled in the margins of a used textbook.
Wow, so that leftover bit. Have you seen cases where that tiny piece of Slack data actually cracked a case?
I can think of several generalized instances, yes, where maybe a fragment of a password or part of a deleted document found in RAM Slack provided the crucial link investigators needed. It proves no space is truly wasted from a forensic viewpoint. And how FAT deletes files is also super important. When you delete a file in FAT, the OS doesn't wipe the data. It just marks the file's entry in the directory table with a special character, usually HEX E5, and it zeroes out the file's chain in the FAT table itself.
So the data's still there?
The data itself. It's still physically sitting there on the disk platters in what's now marked as unallocated space. It's just orphaned.
Yeah.
Waiting to be overwritten by new data eventually. But until then, it's potentially recoverable.
A huge vulnerability for someone trying to hide something, but like you said, a gift for an investigator. How did NTFS, the new technology file system, change things? Did it make recovery harder or handle deletions differently?
NTFS, which came along with Windows NT and is still the main system in Windows 10 and 11, was a massive step up from FAT. It stores way more information about files, gives you much finer control over permissions and such, and crucially, it's a journaling file system.
Journaling, what does that mean practically?
It means NTFS keeps a log, a journal, of changes before it actually writes them to the main file system structures. This makes it much more resilient to corruption, say, if the power cuts out suddenly. While it still uses clusters, NTFS is generally more efficient. It tends to result in less file slack, especially on smaller drives where it uses smaller clusters. And another big plus was native support for Unicode. UTF-8, UTF-16, meaning it handles international characters properly, which FAT struggled with.
Okay, so if FAT has the file allocation table, what's the core directory structure in NTFS? You mentioned the master file table, the MFT.
Exactly. The MFT is conceptually similar to the FAT, but much more sophisticated. It's actually the first file on an NTFS volume. It contains at least one record for every single file and folder on the volume. The first 15 or so records are reserved for NTFS's own system files, the metadata files that manage the file system itself. Now, how files are stored in these MFT records, each is 124 bytes, is key. The record is divided into attribute IDs. If a file is really small, its data might be stored resident, meaning directly inside the MFT record itself.
Wow, the whole file.
The whole file's data, yes, if it fits. But for larger files, the data is non-resident. The MFT record then just contains pointers, essentially. It points to data runs which list the actual logical cluster numbers, LCNs, out on the disk where the file's data is stored. This resident versus non-resident distinction matters because you might recover resident data even if the main file clusters are damaged or overwritten. We also have to watch out for things like NTFS alternate data streams, where extra hidden data can be attached to a file, and NTFS compressed files, though most forensic tools handle decompression easily.
That's incredibly detailed. So many places data can exist. What about deliberately hiding it with encryption? Let's talk about the NTFS encrypting file system, EFS. How does that work? And can investigators get past it?
EFS came in with Windows 2000. It lets users encrypt individual files, folders, or even whole volumes using public and private key cryptography. The critical forensic element here is the recovery certificate. When EFS is first used, Windows usually generates this special certificate and assigns it to the local administrator account, or a designated recovery agent. This means an administrator with the right credentials can often decrypt EFS-protected files, even if the original user lost their key or forgot their password.
Ah, so there's potentially a built-in way in.
Potentially, yes. Admins can use command line tools like Cipher and Copy to manage and use these recovery keys. It's not always simple. You need access and the right setup, but EFS isn't necessarily a dead end for forensics if that recovery mechanism is in place.
Good to know. Okay, so we talked about deleting in FAT. How does it compare in NTFS? If I delete a file, does it also just hang around in unallocated space?
It kind of depends how you delete it in NTFS.
Yeah.
If you use the normal Windows interface, like dragging it to the recycle bin or hitting delete in File Explorer, it usually just goes to the recycle bin. It's tracked by a hidden file called info2, and it's easily recoverable until you empty the bin.
Okay, standard stuff.
But if you use the old MS-DOS command prompt and type delfilname.txt, that behaves much more like the FAT deletion. It bypasses the recycle bin. The file's entry in the MFT gets marked as unused, but the actual data clusters, they're left untouched on the disk, becoming unallocated space, just like an FAT, waiting to be overwritten.
That's a really important distinction, command line versus GUI deletion. Okay, and briefly, looking forward, Microsoft also created ReFS, the resilient file system. What was the goal there? Is it replacing NTFS?
ReFS came out mainly for Windows Server environments, starting with Server 2012. It's really designed for huge amounts of data, think massive storage arrays, cloud backends. The main goals were maximizing data availability, improving integrity against corruption, and scaling way beyond what NTFS was originally built for. It uses structures similar to the MFT and uses B+ test trees for organizing data, which makes accessing really large files very fast. It's not really replacing NTFS on regular desktops and laptops yet, but it's Microsoft's answer for big data storage needs. It focuses more on preventing corruption in the first place.
Makes sense. Okay, shifting gears slightly, but related to data protection, whole disk encryption, WDE. With laptops getting stolen, losing PII or trade secrets is a huge risk. WDE seems like a major defense. What are its key features and the challenge for investigators?
WDE is definitely a strong defense. Tools doing this encrypt every single sector on the drive, including the boot sector itself. Key features usually include pre-boot authentication. You have to enter a password or use a token before Windows even starts loading. They use strong, industry-standard encryption algorithms and have robust key management. The big challenge for forensics is simple. If you encounter a drive encrypted with WDE, you can't just hook it up and browse it. You need the decryption key or password. Often, you'll need to use the specific vendor's software or recovery tools, assuming you can legally compel the release of the key or password to decrypt the drive before you can even begin your forensic analysis.
So access is the main hurdle. Are there common WDE tools we should know?
Sure. Microsoft's own BitLocker is very common, especially on business editions of Windows. It often ties into the computer's TPM chip for key storage, adding another layer. Then you have lots of third-party options like Symantec, endpoint encryption, Voltage Secure File, Jetico Bestcrypt, many others. They all fundamentally do the same thing, lock down the entire disk until authenticated.
Right, creates a significant barrier. Okay, let's move inside Windows itself. The Windows registry, people always call this a forensic goldmine. Why? What's actually in there?
It truly is a goldmine. The registry is this huge hierarchical database where Windows stores, well, almost everything about its configuration and activity. Hardware settings, software installations, network connections, user profiles and preferences, recently opened documents, USB devices that have been plugged in, typed URLs, the list goes on and on. It's organized using terms like HKEYs for the main sections, then keys, subkeys, and individual values holding the actual data. Certain files containing parts of the registry are called hives. For investigators, it's invaluable because it tracks user actions and system changes over time, often leaving traces that users thought they'd erased. Tools like FTK or Always Forensics really help navigate it because manually reading it is intense.
A timeline of activity, basically. That makes sense. And if the registry is a timeline, then understanding Microsoft startup tasks must be crucial too, right? For figuring out when a computer was last used.
Absolutely critical for establishing timelines. Knowing the sequence of events when a Windows machine boots up helps you interpret timestamps correctly and understand what processes were running. There's a difference between, say, Windows Vista and later, version 7, 8, 10, 11, versus the older NT-based systems. Vista and newer use a boot configuration data BCD store to manage boot options, which you can view with tools like BCD Editor. They also shifted to using EFIU EFI more heavily and replaced older boot files like NTLDR with newer ones like bootmgr.exe, winload.exe, and winresume.exe.
And the older systems, like Windows XP, which we still sometimes encounter, what files were key there?
For XP, you'd look for NTLDR, the bootloader, boot.ini, boot options, bootsec.do, so dual booting, ntdetect.com, hardware detection, ntoskrnl.exe, the kernel, hal.dll, hardware abstraction layer, pagefile.ss's virtual memory, and various device drivers. Now here's a really important forensic warning about Windows XP specifically, especially on NTFS. When an XP machine starts up, several of those core system files get accessed, and guess what? Their last access timestamps get updated to the current time of the boot.
Oh no, so it overwrites the actual last access time.
Exactly. It can destroy crucial evidence about when the computer was truly last used by the suspect. You can't always trust those last access times on system files on a booted XP machine. It's a classic forensic trap.
That is a critical warning. Wow. Okay, one last major topic. Virtual machines, VMs. These seem like powerful tools, but how do they fit into digital forensics?
VMs are fascinating. A virtual machine lets you run a complete operating system, the guest OS, inside a window on your existing computer, the host computer. It does this by emulating hardware. What's interesting is that a whole VM, which looks like a real computer, is actually just stored as a set of files on the host machine, and the guest OS is always limited by the host's resources. The big forensic application is creating a safe environment, a sandbox. You can take a forensic image of a suspect's hard drive and restore it onto a virtual machine. Then you can boot up that suspect environment inside the VM, run programs, analyze files, even run malicious software the suspect might have used, all without any risk of changing the original evidence drive. It's incredibly useful for analysis.
That sandbox idea is brilliant for evidence integrity. But you hinted VMs could be a challenge too. How so?
Well, like many technologies, they're dual use. From a network forensics perspective, VMs can be used to stage attacks. Someone could set up a VM, use it to launch an attack on another system or network, and then just delete the VM files. It can make tracing the attack back harder if logging isn't great. Popular VM software includes things like VMware, VirtualBox, Microsoft's Hyper-V. People use these all the time, often creating VMs from standard ISO installation files. Just always remember that VM is contained within and limited by its host.
And that wraps up our exploration today. We've covered a lot of ground, haven't we? From the real basics of disk drives and file systems like FAT and NTFS, digging into encryption like WDE and EFS, understanding the treasure trove that is the Windows registry, nailing down those startup processes, and finally looking at how virtual machines play a role.
Absolutely. And hopefully this gives you, especially you future forensics pros, a much clearer picture. Understanding this stuff, where data hides, how the OS manages it, That's what lets you methodically pull out the facts. It really is about equipping you to, well, expose the truth in the digital evidence. Knowing the foundations is how you do it effectively.
Couldn't have said it better myself. Thank you so much for joining us on the deep dive today. We really hope diving into Chapter 5 of the Nelson and Stewart text this way has given you a solid, practical understanding of these core computer forensics concepts. Okay, before we sign off, here's something to think about. Given all this talk about hidden data, slack space, alternate streams, registry artifacts, what's one area of digital evidence you personally find the most intriguing or maybe the most challenging to uncover? And why? Drop your thoughts in the comments. We'd genuinely love to hear them. And please, one last reminder, like, subscribe, follow, share this deep dive. Help others get this crucial knowledge too. We'll catch you next time on The Deep Dive.